Hello, I'm Anurag Penson. I'll talk about the Lagrangian of the electromagnetic field. So the Lagrangian for the electromagnetic field is the one described in equation 11. We have a factor of mu naught here, which will keep on showing up throughout the calculation. So for simplicity, we can switch to natural units in which c, mu naught, and epsilon naught all become one. So we do not have those factors moving around. And the Lagrangian looks as follows. Here, J mu is the 4 current density, A mu is the 4 vector potential, and F mu nu is the field strength tensor, which is defined as follows. So as you can see from equation 13, the definition of the field strength tensor, you can see that it is a completely antisymmetric tensor. So it will have no diagonal elements. Diagonal elements will be zero, and upon computing it, we can find that the zero I components are the electric field components, and the ij components are the magnetic field components. So over here, the field strength tensor we can see is invariant under a gauge transformation of the form del mu psi, which is essentially adding the 4 gradient to the vector potential, and it doesn't show up in the new field strength tensor because the partial derivative is commute. Now, so we can look at the we can consider the we have to consider the action, the change in the action brought about by this gauge transformation, because in the end, what we have to do is sort of extremize the action, and action is the integral over d4x of this Lagrangian. And so the additional term that will show up is the j mu del mu psi, and so over d4x. And you can see that using integration by parts, you can switch this divergence term onto j mu, and the 4 divergence of j mu is 0, which is just the continuity equation. Now, deriving the Euler-Lagrange equation of motion from this Lagrangian is a rather straightforward calculation, and it is described here from equations 17 and 18. In these steps, we can see how we get the non-homogeneous Maxwell's equation. The homogeneous Maxwell's equations, which are the curl of E and the divergence of B equations, those come about from the antisymmetry of F mu nu, from its definition itself. So checking the second equation of equation 16 is rather trivial, and this is known as the Bianchi identity. It can be formulated in a more compact form as equation 20, where the dual field strength tensor is defined as follows. This definition it can be generalized to higher manifolds and different metrics as well, and it's known as the Hodge dual. But in this case, which is Minkowski spacetime, the dual is defined by equation 21. So this equation 20 is the homogeneous Maxwell's equations, and equation 18 is the non-homogeneous Maxwell's equation. Thank you.
Hello everyone, I am Mehul and now we're talking about section 2 of our REAM project, which talks about the Lagrangian and how we can incorporate the effects of photon mass into it. So in all of the theory that we've done before this in the previous section and all of the content we've discussed in the course, we never really assumed that photon can have a mass, and we just went through with it. So now what we're trying to do now is incorporate a mass term in the Lagrangian, which we derived in section 1. So how we do that is by incorporating a term like this, and the reason why we do it is given in more detail in the report itself, so we can glance through it, but this is how we actually try to incorporate the mass term. So once we have this Lagrangian, this new Lagrangian here with mu acting like a mass term, you can see the relation between the photon's mass and mu here. One important thing to note here is that as mu tends to 0, so will the mass of photon and vice versa. So we can just say that, okay, whenever I want to set the mass of photon to be 0, I can just set mu to be equal to 0. So now once we have this, what we try to move on to is the Maxwell's equations. So the homogeneous Maxwell's equations remain the same because they only rely on the antisymmetry of the field tensor. and addition of this mass term does not really bring a change to that. So that term part term is the same, and the new source terms which you obtain with the help of the Euler Lagrange equations of motion, they have a modification added to them, which is this term of mu square a nu. Also, just as a sanity check, we can try putting mu equals to 0, and we see that okay, we return exactly what was there before in the case of a massless photon. Now, assuming the Lorentz gauge and then also considering the electrostatic case, we obtain this equation for a sub nu, and when we specifically try to solve for the electrostatic potential, this is what we get, this phi of r. So you can see that this is very similar to the Coulomb potential, except that there is one new term here, which is e raised to minus mu r. And again, as a sanity check, we can just try putting mu here as 0, and we just obtain our original Coulomb's law. So this all agrees with the case of massless photon. And the dispersion relation in free space for vacuum will be given by this relation. And again, you can check by putting mu equals 0 that we obtain the relation which we already know exists for our current electromagnetic theory of massless photons. Okay, so now this is all well and good, but we also have to understand if there is some way to devise an experimental method to measure this mu, or actually the mass of a photon. So in a 1971 APS letter, P.A. Franken and J.W. Ampelsky, two scientists, suggested a tabletop experiment to determine the photon mass. What they really mean by tabletop is that no very sophisticated machinery or experimental setup is needed for this. They wanted to do it in as simple a way as possible. So just stating a few results. This is the relationship which they assume will be true for the case of the phase velocity of light uh, and the phase velocity in the case of massless photons. This is the relationship that they've assumed. And what they do is that ask you to consider a resonant cavity such that its resonant frequency in the case of massless photons is omega naught, and in the case of massy case is omega dash. And what they also say, or which also seems true, is that the value of k, which is the wave vector for the various resonance frequencies, they will actually just depend on the geometry of the cavity, and this seems very logical. So it doesn't really uh, matter what is the mass of mu or the mass of photon that we assume. So assuming this to be true, this is the relationship which we find between the phase velocity of light in a massy case and the different frequencies. And combining the equations 30 and 31, this is the dispersion relationship which we obtained, and this looks like exactly the same as the one before, just replacing omega naught, just replacing ck with omega naught. So let us just try to see what this relationship is trying to tell us. So here, basically, if we are able to find a cavity such that its omega naught is 0, or if we take a cavity which has its omega naught tending to 0, we will be able to determine its new massy photon resonance frequency, which is omega dash, and that will give us an idea about the value of mu. So how you try to get omega dash to be very small or near 0 is that you choose larger and larger resonant cavities, which is not physically feasible. So what we do here is, instead of trying to talk about resonant cavities, we consider RLC circuits. And what we do is we try to think of a way to check, if we can get some sort of mass term here in an RLC circuit equation, and see if we can then, devise ways to calculate it. So what they just did was they consider an RLC circuit such that its resonance frequency is given by this value here. So this is the case, or the resonating frequency of a decaying transient. So this is what they have assumed, and what they think is that okay, in the case of massy photon, the dispersion relationship will just change by this factor of mu square c square, which is what we had obtained earlier in the case of resonant cavity. Or this is what they at least assume in the case of a resonant cavity. So they just assume that this should stand true, and they say, okay, if we can set L, the product of LC, to be very high, and also select a high quality factor which works on this second term here. So that is, if we have a very high quality factor, the second term becomes very small and tends to 0. They say that okay, if you have something like this, then we can again, using the same logic as before, try to get an idea of the value of mu here. So they just performed this whole process and obtained an upper bound of 10 raised to minus 49 grams on the mass of a photon. Right? This is what they have. But now if you think about it, the assumptions aren't really very thorough or they are on very shabby ground. So just assume, okay, this should stand to, this should stand to, this probably stand to. And that actually results in problems. And this is highlighted by David Park and E.R. Williams in a later. And also, yeah, they haven't really talked about, what the how the magnetic and dielectric properties of the materials vary and how that will have an impact on this measurement of mu. So what Park and Williams say is that whatever they have done before is actually incorrect, or at least does not give the or gives a very wrong estimate of mu. So what they say is that consider a cylindrical traveling wave tube. It doesn't really matter what a traveling wave tube or TWT is. What is important is that TWT has helical paths along its boundaries such that they offer zero resistance to any current flowing through them. So we assume that the radius of the tube is A and the angle the helices make with the circumferential is psi. And in order to create a resonator, this is just a cylindrical tube. In order to create a resonator, they just close it and make a toroid out of it. And the circle of circumference, the toroid is L. We just do a small bit of math, and what they finally obtained is this dispersion relationship for this TWT, where D is defined in this way. And now what they do is compare this dispersion relationship with the ones that Frank and Ampulsky used before. So in the assumption of a very small a, and by again using geometrical properties and determining k, this is the result that they get for small values of a. This is the value that they get when they talk about first order in mu square. And you can see that this is very much different from the relationship that Franken and Ampulsky used before. So this is how Park and Williams say that, okay, the dispersion relation itself used was wrong, and therefore the bound that Franken and Ampulsky had obtained was actually very, very wrong. The point to notice here is, I'll just specify what the main difference is that here if you assume this to be, the omega naught, as omega naught tends to 0, your omega dash tends to mu square c square, and that is that allows us to determine the value of mu. But in the dispersion relationship which we have obtained here, you can even when omega naught tends to 0, irrespective of the one Franken and Ampulsky suggested, you'll actually you'll be unable to measure the value of mu. And therefore, what David Parker and Williams say is that instead of going about it like this, what we should really try doing is trying to measure the fractional differences between omega dash and omega naught square. And to even do that, we'll have to consider cavities, or say in the case of this, the TWT resonator, which is very, very, very large. This mu, since the fractional difference is of the order of mu square, we'll have to try and figure out some way to get very, very large L's. What Park and Williams also say is that, okay, although the math they have done is for the case of a TWT loop, which is different from RLC, they say that similar analysis can be done for that case, and the results which they obtain for that should also not be very different, which also seems logically true. I mean, although they are different on the surface, all of the characteristics of resonators should be similar, and therefore the result that they've obtained here should also apply, if not directly applicable, in some way to the result of an RS circuit. And therefore, what Franken and Ampulsky have done is probably wrong. So yeah, that is it. So therefore, the methods devised by Frank and Ampulsky is not wrong, and what we really should be trying to use is the one suggested by Park and Williams. And this has actually been tried and used, and they have obtained some bounds of the order of 10 to minus 40. Also photon, but not an exact value, obviously. So yeah, that's it. Thank you.
Hi, I'm Shashwat, and I will be talking about superconductivity. So it is a phenomenon demonstrated by certain materials at very low temperature or very high pressure. So what happens is basically that the electrical resistivity that the material offers vanishes as the temperature drops below a certain threshold called the Curie temperature. Now, a subtle point that has to be noted is that we cannot simply model a superconductor as an ordinary electrical conductor with zero resistance, because as the material enters the superconducting state, several electromagnetic properties drastically change. So one such effect, known as the Messner effect, is what we'll discuss, because that is what is related to the Lagrangian formalism, or basically the photon mass effect. So we'll discuss Messner effect next. So Messner effect is basically that when the temperature of the material is above the Curie temperature, it behaves normally, as we know. So it offers a finite resistance. But the moment the temperature drops below Tc, the material transitions to the superconducting state and the resistance vanishes. But what happens is that some magnetic properties change as well. So the like in the T greater than Tc regime, the material behaves as a paramagnet, or it allows the magnetic field lines to pass through it. But uh, as the material enters the superconducting state, it expels out the magnetic field lines or starts behaving as a diamagnet. Now, in order to explain this effect, uh, London brothers proposed a theory called the London theory, and it is like a classical theory, and it was given in 1935. It is a classical theory, and it is fully non-relativistic. So, let's start with the discussion. So, uh, first, let me state the assumptions that let me state the notation basically. So Q represents the charge of the charge carriers, and NQ represents the number density. V vector over here is the velocity, and J vector is of course the current density. So we know that J vector is Q NQV. So we start with this equation. Now, uh, once again, we know that when there is electromagnetic coupling, the canonical momentum is related to the kinetic momentum. As such, capital P vector is small p vector plus q a by c. So capital P vector here is the canonical momentum, and the small p vector is the kinetic momentum, and a vector is of course the vector potential. Now, this is where London brothers made an assumption, made a very sort of radical assumption at the first sight, that the superconducting state is a coherent state of charge carriers with zero canonical momentum. So this assumption cannot be easily justified using purely classical mechanics, but it turns out that there is a justification of this assumption in like, when we treat the problem quantum mechanically. So of course, now since we are in the non-relativistic regime, we can also write P vector like kinetic momentum as mq times v vector. So we finally get this equation 42. Capital P vector is equal to mv plus qa by c. Now, I'll just briefly chalk out the quantum mechanical discussion. Of course, the more detailed version of this is given by BCS theory, but detailed discussion of the Bardeen-Cooper's three-foot theory is beyond the scope of this project. So I'll just briefly talk about the proof. So it starts with a very well-established theorem in condensed matter physics and semiconductor physics known as Bloch's theorem. So it states that if we have a periodic lattice potential, the wave function, the solution to the Schrodinger equation can be given as such. Psi block is equal. Psi block represents the Bloch wave function. It is equal to e to the I k dot r u of r, where u of r is a function with the same periodicity as the potential, capital R vector in this case. Now, uh, in the absence of the electromagnetic field, of course, the uh, average value or the expectation value of the canonical momentum is zero. Here, P vector represents the canonical momentum operator. And this can be understood classically as well, because when there is no field applied, of course, the velocities of the particle is randomly distributed and they average out to zero. But when we apply a electromagnetic field, we expect this expectation to change. Now, and that happens in most of the cases, even in the normal regime, or when the material is in its trivial or normal state, that is T greater than Tc, of course, this expectation is non-zero. But when the material enters the superconducting state, the wave function becomes rigid. Now, this uh, rigidity again cannot be explained in detail in this presentation, but yeah, so I'll briefly chalk out how it is obtained. So rigidity of a wave function means that even after the application of an electromagnetic field, the expectation of the canonical momentum remains zero. So here I'll talk about BCS theory. So what basically is done is we uh, treat the problem purely quantum mechanically. That is, we write the Schrodinger equation and we somehow solve it. So the first step is to model the lattice. So we take a finite lattice or a lattice with a periodic boundary condition, whatever. So we take a finite lattice and we write its Hamiltonian in a discretized fashion. After we do that, we take its Bannier transform, which is like a discrete Fourier transform from the x space to the y space. Then the Bannier transform is of course expressed using the spin orbit coupled uh, creation and annihilation operators, which are represented by C and C dagger usually. And after that, now the Hamiltonian contains delta terms or the gap terms, which act as non-diagonal elements, and we need to first diagonalize the Hamiltonian. But for doing that, we need something called the Bogoliubov transformation. So for this transformation basically is that we introduce new quasi-fermionic creation and annihilation operators, which are simply the linear combinations of the electronic ones. And these new quasi-particles are called Bourgeois bonds. Now, the ground state of the once we have diagonalized the Hamiltonian, it is quite obvious that the ground state of the Hamiltonian can be thought of as the vacuum in the Bourgeois bond space, right? So once we have diagonalized the Hamiltonian, we apply the perturbation theory, and from that, what we get is the expectation value of canonical momentum turns out to be zero naturally. So this is a brief overview of what has to be done in quantum, in the quantum treatment of superconductivity. Now, the current density. Now that we have justified the assumption, let's use it to further simplify the expression. So J vector. Now, in this expression, basically the left hand side is 0 in 42. So we know that V vector is equal to minus QA by MC. Now we just substitute that in the J expression and we obtain this. After that, we uh, substitute the expression for J vector in the Lorentz gauge equation for electromagnetic vector potential, and we obtain equation 46. After a little rearrangement, of course, we can see that the equation takes the Proca form. So the Proca form was discussed in the previous section. So here mu is closely related to the finite photon mass, and that will be discussed later. So we define mu as the square root of the right hand side in equation 46, of course. And let's take the static limits first. So in the static limit, A vector does not change with time. So del partial A with respect to t square is 0. So that basically leaves us with this equation, nabla square A is equal to mu square A. Now we know the solution of this equation is of the form of exponential in nature, that is e to the power plus minus mu x. Now if we take the size of the material to be much larger as compared to the length scale corresponding to 1 by mu, we can ignore the e to the plus mu x solution because we don't want the solution to sort of blow up, and that leaves us with an exponentially decaying solution. So the reciprocal of mu 1 by mu, that is defined as lambda L, or the London penetration depth, and it can be clearly seen that beyond a few lambda L's, of course, the potential becomes very small. So it kind of gives us the idea, kind of explains the Messner effect. But in order to make any further inferences, an order of magnitude estimate of lambda L is important to see how small it is exactly. Now, before we move on, it's important to note that as discussed in the previous section, the finite photon mass m gamma is related to mu as h cut mu over c. So from here we can estimate m gamma as h cut upon c lambda L. So Messner effect basically turns out to be a consequence of finite photon mass effect. Now, before in order to make an order of magnitude estimate of lambda L, we need certain inputs from PCS theory, and of course they are supported by experiments as well. So the inputs are as follows. The first one is the charge of the charge carrier is minus 2e. That is, the conduction in the superconducting state is because of loosely bound pairs of electrons known as Cooper pairs. Now Q is equal to minus 2, and of course the mass of the charge carriers becomes twice that of the electronic mass. Now the density of superconducting charge carriers is temperature dependent, of course, because the Cooper pairs form below the Curie temperature. So as the temperature tends to 0, NQ is N, that is all electrons participate in the conduction. But as the temperature approaches Curie temperature, the charge density NQ, that tends to 0, that is no more Cooper pairs are there. Now we take NQ to be of the order of 10 to the 28 meter minus 3, because that is the typical charge number density in metals, and that basically gives us that lambda L is of the order of a few tens of nanometer. Now that is quite less as compared to a millimeter or micrometer sized sample. So this basically explains the Messner effect. Now so a simple diagram is shown here. So in this figure we can see that when T is less than Tc, that is the material is in its superconducting state, it does not allow magnetic field, and the graph over here shows the exponential decay of magnetic field B. So next we look at how we measure London penetration depth. So the measurement scheme is quite straightforward. What we do is we put the sample in a series with a resonant LC circuit, and we change the temperature. Now, with the temperature, the resonant frequency of the circuit changes. The shift in the frequency basically encodes the time dependence of lambda L, and it is seen that in the long wavelength limit, the surface impedance of the circuit is purely reactive. That is ZS, the surface impedance, which is given by the ratio of the tangential electric and magnetic fields. So it is given by minus I 2 pi by C epsilon naught lambda L over lambda, where lambda is the wavelength of the lambda is basically the wavelength. So that's pretty much it.
Hi, Devashish here. I'll be talking about the canonical stress tensor for electromagnetism and conservation laws. So just a brief recap of small part of classical mechanics. So if you're given a Lagrangian for a system, then we could like transform to the equivalent Hamiltonian formalism using the canonical transformation, which is given as follows. In case of a local field theory, the total Lagrangian of the system is the integral over all space of a Lagrange density, which is given as above. So it's a function of potentials and its derivatives in case of electromagnetism. Similarly, we can define the Hamiltonian density as follows. And the Lagrange density for electromagnetism is this, which was introduced earlier. The canonical transformation used to define the Hamiltonian density looks as follows. This is the covariant generalization of this transformation. So it essentially has the same form. The only thing is QIs are now replaced by AIs, and yeah, we have four so space-time derivatives. Here G alpha beta is the Minkowski metric with negative signature, so +1 followed by 3 -1s in the diagonal. To get a more physical understanding of what this tensor actually is, we can write its components, which look like this. So yeah, we can write the Lagrangian in terms of electric and magnetic field, and the components look. So the T00 component actually has the energy density as its first term, followed by a divergence term. Similarly, the T0I component has 1 by C times Poynting vector plus a divergence term. So yeah, so for localized fields, we can always set the space integral of the divergence terms, or like surface integral at infinity to be 0. So what we get is the total energy and the momentum of the field if we integrate the components here. So this relation between U and the component T00 and the relation between the Poynting vector and the component T0I hints that there should also be a generalization of this theorem, the Poynting theorem. Again, just a reminder, this is source free. Everything is source free right now, so we don't have a source term on the RHS. So this can be generalized in terms of differential law for the stress energy tensor T alpha beta. So the 4 divergence is 0. Now the proof for this is straightforward. I have worked out the math over here. We only need to invoke Euler-Lagrange equation of motion in between in one step, and then we can easily show that the 4 divergence is 0. So we have actually worked out the energy and momentum conservation for the fields in the source free case. The tensor T alpha beta is not yet what we are looking for, because it lacks symmetry. T0 is obviously not equal to Ti0 if you look at the form. This also leads to this leads to one problem, that the conservation of angular momentum doesn't pop out naturally. You can have a look at the report to go through this part. That is not really important. The important thing is we want to construct a symmetric, traceless, and gauge invariant stress tensor. So we start with the tensor which we had written, the expression for the tensor T alpha beta. We write the Lagrange density in terms of F mu nu. Then yeah, we can so F beta lambda would be del beta A lambda minus del lambda A beta. We use that in this term to write it as two terms. First with in terms of F lambda beta times something which is subtracted to get back the above term. So now the second term here is what we need to analyze, because the first term exactly has the form that we wanted. It is symmetric, traceless, and gauge invariant. Yeah, simple analysis shows that the second term actually has can be like the integral over all space of the second term is 0. Also, the four divergence is 0. Which is why if a conservation law holds for T alpha beta, it should hold for this guy. Which means we can now define the symmetric, traceless, and gauge invariant tensor, which we were looking for in the first place, as this. It has a familiar looking components. The first one being purely the energy density of the fields. The T0I components, that is the first, the next, like the three elements of the first row and the three elements of the second row following U are actually the components of the pointing vector S upon C. C is the speed of light. And the space-time components are something that we had actually worked out in class. So we had worked out Tij, which was in terms of B. We started with the conservation of energy and then conservation of momentum and worked this out using, yeah. So we actually arrived at the same thing naturally. And the conservation law then becomes the four divergence of theta vanishing, contracted over the first index. Yeah, this encodes the pointing theorem as well as conservation of field momentum if no sources are present. Now, if we include sources, that is currents and charge density. So this is the current 4 vector, which is composed of the current density followed by the 3 vector. Then we expect the divergence of theta alpha beta 4 divergence to be non-zero. And we don't need to explicitly find out what it is. So yeah, this is some math. You could go through it later. I won't discuss it in detail. So the 4 divergence can be computed as follows. What I invoke here in between is the Bianchi identities, which is the property of the antisymmetric nature of F. Also, I've used the inhomogeneous Maxwell's equation, which is that the 4 divergence of F mu nu contracted over one index. So del mu F mu nu would be J nu. J nu is the current. So that actually gives us the relation stated here. So now the 4 divergence has some source term. So the right hand side acts like a source term. And if we write out various space-time components, then we actually retrieve Poynting's theorem with the source term, J dot E included now. Then we get the momentum conservation law. In fact, this is what we started with in class. So we started with the RHS, which was the Lorentz force law. We used Maxwell's equations to get the LHS. Now we have done the reverse. So not reverse, we actually naturally got both here. So the right hand side for the above equation can now be combined in a covariant way to get a force density 4 vector. Not really important, just a definition for convenience. And yeah, so the above integral form of the above law can be written as follows. So the conservation law for total energy momentum content of the field plus particle system. Okay, so now we come to a more interesting part. So this is Noether's theorem. It states that for every continuous transformation of coordinates or field functions that leaves the action invariant, which means it would in turn leave the Lagrangian invariant in some sense. There corresponds a conserved current. So this would correspond to our conservation law, which we derived earlier. And there's a very natural way to working out the conservation law. So here I've chalked out the procedure for obtaining the conservation law. Due to limited time, I request you to go through it on your own. I'll directly go to an example which perfectly demonstrates how to do that, go through the procedure. So the example is that of a translation of both the source and the electromagnetic field. So basically we translate the whole system in an arbitrary direction along a vector n row, 4 vector. And then perform a gauge transformation chi. So we are free to choose what chi is, because we expect it not to affect the equation of motions. So the change in the vector potentials, sorry, not the vector, the 4 vector potential is given as follows. This is straightforward. Now, since we are free to choose chi, we choose chi such that the variation in the 4 potential is gauge invariant. So delta A mu would have this form. Yeah. So moving forward, now we need to find out the change in the Lagrangian. So the change in the Lagrangian, yeah, it's straightforward. Since the Lagrangian is a function of the field and the derivative of the field, the change can be expressed as a change in some derivative times the change in the field followed by some derivative times the change in the derivative of the field. Sorry if that wasn't very clear, but yeah. So what we end up with is only one term, complete derivative, 4 derivative, and 4 divergence. That is what I've done here as well. Now we substitute the expression that we got for delta A alpha. The only thing that I've done here is raised and lowered a few indices that I can do by multiplying copies of the metric. And yeah, so some simple math gives us this. Okay, so now we have 2 copies of f, which actually looks like a part of theta mu beta, which is why I've added and subtracted a term. So this term actually completes theta mu beta, and then like this term added to the above expression. And then we need to analyze the remaining term. What does it mean? So, and yeah, just note that this is 0 irrespective of what we choose n beta to be, which means the quantity inside the square brackets must be 0. And that is actually our conservation law. Let's see if we get the original law which we had derived a few sections back. So this partial derivative can be written as follows. I've then used the Bianchi identity to write it as 2 terms. The first derivative over here. And then I've used chain rule in reverse. So I combined 2 terms and like subtracted the extra term which we get. I've done this because it's actually convenient. 2 terms actually cancel out because in the first and third term, if you see sigma and tau are dummy indices, and one of them differs by a swap of indices, and f mu sigma would be minus f sigma mu. So yeah, and what we have left is f times 4 divergence of f, and Maxwell's inhomogeneous equation just says that it's j. So yeah, if you see, we actually got back the force term which we had derived in equation 62. Yeah, so this is our conservation law. So simply by imposing that under the symmetry of translation and gauge invariance, our Lagrangian should remain invariant. We got the conservation law. So that is it. Thanks.
In this section, we'll look at the covariant form of the wave equation and its solution in terms of Lorentz invariant Green's functions. So we start off with the non-homogeneous Maxwell's equation in terms of the electromagnetic tensor F alpha beta and the 4 current J beta. And then we expand the definition of F alpha beta as del alpha A beta minus del beta A alpha. And we write that and then use the Lorentz gauge to end up with the covariant form of the 4-dimensional wave equation with the source term J beta, and here it is on the left hand side is the D'Alembert of the 4 vector potential. So we solve this by constructing the Green's functions dx x dash for the wave equation, where x dash are 2 points in space time. So the Green's function satisfies this differential equation in terms of this 4-dimensional delta function. And since the medium is unbounded and there are no boundary conditions given, the Green's function has to depend only on the difference of the 2 spacetime points x and x dash. So we compactly write z as the difference between the 2 points x and x dash, and the Green's function equation is written as D'Alembert of z times dz equals del 4z. So now we use the routine approach of finding out the Green's functions first in the wave number space and then Fourier transforming back to the real space, so that we can now convert this differential problem to an algebraic problem. So we take the 4-dimensional Fourier transform of dz in terms of the wave number, and here in the exponential k dot z, here this k dot z is the inner product in Minkowski space. So this is k naught z naught minus the 3 vector dot product of k and z. And similarly, if we take the Fourier transform of the delta function,
and substitute these in the differential equation and obtain the Green's function d twiddle k in the wave number space as this. And now we have to evaluate this, substitute this back in the expression for dz, and we need to evaluate this integral over d4k. Now, this integral has to be handled carefully because this k dot k, the denominator has singularities, which should be taken care of. So we first split this into the integral over dk naught and over the 3 vector k. So when we write it in this form, this denominator is essentially k naught square minus kappa square, where kappa is the magnitude of the 3 vector k. And this integral has singularities and k naught equal to kappa and minus kappa. So when a situation is like this, we usually consider k naught as a complex variable and integrate over a contour in the complex plane. So now consider the complex plane defined by k naught and consider two line segments R and A. And here are the singularities kappa and minus kappa. So when we consider the integral, suppose we take the line segment R. Now there are two possible choice of contours. We can close the line segment R at the upper half plane or the lower half plane, depending on the sign of Z naught. So this is because if Z naught is positive, the exponential e to the minus k naught Z naught will blow up in the upper half plane. So if Z naught is positive, we have to close the contour in the lower half plane. And exactly the opposite holds for Z naught. So suppose if Z naught is less than 0, then the contour is closed in the upper half plane. And since there are no singularities here, this Green's function vanishes. But if there is more than 0, then we close it in the lower half plane, and this encloses two singularities. And so we have to use Cauchy's residue theorem to evaluate the integral. And by doing that, we end up with this expression. So the k naught part is integrated out, and we are left with the three-dimensional integral. So this Green's function is based on the choice of contour R. So we denote it as dr, and we'll see that this drz is essentially the retarded Green's function. So for the three-dimensional integral, we convert this to polar coordinates first and integrate the angular parts, and then treat these sign terms in terms of exponentials, and that again gets converted to delta functions. So the retarded Green's function is expressed in this form: a causal term in terms of if z is more than 0, it's non-zero, and if z is less than 0, it vanishes, as we told, times this delta function. And exactly if we choose the contour A, we obtain the advanced Green's function, where the causal term is minus of x naught minus x stars. And now we express these functions dr and dA, these functions, in a more covariant form by using some delta function identities as given here. And finally, we end up with the covariant form of the Green's function, and we can explicitly check that this is Lorentz invariant. So after obtaining the Green's function, we substitute this into the integral to obtain the solution for the wave equation. So this integral is a four-dimensional integral with respect to the source current J. And here A alpha in and A alpha out are the solutions of the homogeneous wave equation. So this is the solution of the four-dimensional covariant wave equation using Green's functions.
Start. Hello, I'm Anurag, and I'll talk about more applications of the Lagrangian method. So the first one I'll be talking about is quantum electrodynamics. So till now we looked at the effects of classical electrodynamics, especially in section 1. So its extension to the entire electromagnetic field or entire theory of electromagnetic interactions is known as quantum electrodynamics. So the way we start is we have a Lagrangian, which I will be describing. I will not be getting into the actual quantization part of the field. So, however, I will give a small note on it. So before we actually construct the Lagrangian, we'll break it down into smaller parts. The first one being the kinetic term for whatever particle we have. So here I'm considering only one particle which interacts with the electromagnetic field, whose spinor field is given by psi. So I've assumed the spin half particle whose spinor field is given as psi. So the kinetic term for this field is given by L1. It involves the gamma matrices, and so it also involves like psi and psi bar. They're the two conjugate type fields. Now the second term in L2 is the mass term, which describes the mass of the charged particle, and you can see it looks extremely similar to what we had described in section 2 with the Procol-Lagrangian, where we described the mass of the photon. Over there we had a mu. Over here we have psi bar psi. So these terms are sort of they look very similar in the sense that they are quadratic in the field concerned. So yes, from this term the mass of the particle will emerge, and that m, the parameter m used here, is related to that. Now it comes the actual term for the field strength of the electromagnetic field, and that looks exactly like what we had described in section 1, which is -1/4 f mu nu, where f mu nu is just a field strength tensor like as we had defined in that section. So one more sort of term left is the interaction term, which is sort of crucial since we want to observe how the particle actually behaves in an electromagnetic field, and that term looks like L4, which basically is the inner product of the psi bar gamma mu psi term and the a mu term. So this psi bar gamma mu psi term resembles, I would say, the current density. So that gives us the full Lagrangian as equation 83. Next up, I will describe how we actually construct Lagrangians. So before I actually start, one thing I need to sort of note is that we will be describing the construction of I'll be describing the construction of quadratic Lagrangians rather than any general type of Lagrangian, because a quadratic Lagrangian will give a linear theory, which is the case in most situations. Non-linearities to this can be added as non-linear higher than quadratic terms in the fields themselves, as you will see later on as well. But this describes the simplest example of constructing a Lagrangian given the symmetry group, constructing the quadratic Lagrangian. So first off, let me assume a couple of things. Just figure out some notation. The first thing is that let us assume that the symmetry group of the system is the Lie group L. And now keep in mind, I've assumed some general L here, but in most cases it is some product of SUN groups. So most theories are Yang-Mills theories. So their symmetry group is SUN, or a product of or a direct product of those groups. So we denote the gauge fields corresponding to the generators of this algebra by a mu, where each a mu is a 4 vector, and the index a basically indexes these gauge fields. So a goes over 1, 2, 3, 4 to n is the number of generators we have. And let FABC denote the structure constants of the 3 algebra. So the first thing we need to define is a covariant derivative, which transforms exactly like the field. So if a field transforms under some group action, so will the covariant derivative. So covariant derivative of field transforms exactly like the field. And so that is defined by equation 84, where TA are the generators of the field. Now, D is the covariant derivative, like I said. Now we need to describe the field strength tensor for this general theory, and that we define it as given by equation 85. So we have n different field strength tensors corresponding to n different generators, and so that is why we have that index A showing up. So this looks extremely similar to what we had in the case of the electromagnetic Lagrangian, where we only had the first 2 terms out of this. That last term was not there, the reason for which I'll explain soon. Now we begin actually constructing the Lagrangian. The first term we'll look at is the gauge fixing term. So the gauge fixing term is described by equation 86. The next thing we'll need to describe is the actual the complete Lagrangian without incorporating the particle fields themselves. Those particle fields will have their own kinetic terms with the covariant derivative involved in them, but we'll have a look at that in a bit. So here I've changed the notation to f mu nu just to reflect our original notation. This g mu nu is the traditional notation, which is used again later on, as it is used in several papers. The g mu nu is a more common sort of notation, but f mu nu resembles what we had before, so I've used it. And this j mu a mu term is the term which looks at the sources and their interactions with the gauge fields themselves. So keep in mind there is a sum over A here as well. So you will have a current corresponding to each generator. Now, one more important thing to note is that the field strength tensor itself is still antisymmetric. The first two terms are clearly antisymmetric, and the last term, the G F A B C A mu A nu, that is antisymmetric as well because the structure constants themselves are antisymmetric. Now, this antisymmetry of the field strength tensor gives us the Bianchi identity, which is d mu of the dual of the field strength tensor is 0. And so that is described in equation 88 and 89. And the equation of motion, which is just the Euler-Lagrange equation, is given by equation 90. Now, for our theory of electromagnetism, the symmetry group is U1, which is an abelian group, which simplifies our life a lot because since it is abelian, all the structure constants are 0, and there is only one generator. So, since there is only one generator, we only have one gauge field, which is A mu. So I can just drop the index small a. We only have one. So according to our rules, we directly get our field strength tensor as the one we had defined before. And the covariant derivative becomes del mu minus IE A mu. And this term you might have seen already in the quantum electrodynamics part. When you combine the interaction term and the kinetic term, the operator sandwiched between the two, the conjugate field and the field itself is the covariant derivative. So that is where it shows up. It shows up as a net kinetic term, which incorporates the interaction within it as well. So keep in mind that this interaction is not the potential interaction. It is the interaction which shows up in the kinetic term. Now, another theory I will look at is one which describes a form of a magnetic monopole, and that is the 't Hooft-Polyakov monopole. So, and this is a bosonic part of the Georgi-Glashow model of electroweak theory. So the Lagrangian, as you can see, is given by equation 98. One thing you have to note, you can note here is that I have used vector signs over all of the quantities. So the G mu, the field strength tensor, I've described as a vector. The phi field I've described as a vector. So before I actually move on, I'll give the reason for this. That is because the symmetry group of this theory is SO3, and SO3 SO3 has 3 generators, and the way so the net collection of all of our gauge fields and the field strength tensors and the actual fields themselves, they will behave like vectors, normal 3 vectors. That is why I've used the vector sign, where you can see I've described all of these potentials and all of these terms. Here, W mu vector has 3 components: W plus, Z, and W minus, which correspond to which are the gauge fields, and phi is the Higgs field. As I've written here, this is 3D adjoint in the 3D adjoint representation of SO3. Now, after some amount of calculation, quite a bit of calculation and the use of some ansatz, we get a field. We can define a field strength tensor which resembles what we actually had. So we get a magnetic field out of this theory. You can go through all the calculation and you will find that. So we get a magnetic field out of it of the form R over R cube, which is R hat over R square basically, which is like the Coulomb interaction. So it is as if we have a Coulomb interaction of a magnetic monopole somewhere of charge proportional to 1 over E. So it is 4 pi over E, the actual charge. But the point is it goes as 1 over E. And that, as described in the document as well, it basically corresponds to some form of quantization of the product of the minimum magnetic and minimum electric charge. So that quantization sort of gives higher complications to whether or not we can use certain techniques widely used in quantum field theory, but that is irrelevant to our discussion. The last part I would like to describe is where this magnetic monopole actually comes from, and it comes from I would say a twist in the Higgs field itself. So sorry. So as you can see here, we get F mu nu in equation 150 to be the standard field strength tensor which we had before, plus some term in the Higgs field and its derivatives. And the second term being our usual term, if you integrate the magnetic field part of this over some surface enclosing the magnetic monopole, then you would get 0. However, the first part gives non-trivial gives a non-trivial surface integral, and that is where the magnetic charge comes from. And this term looks at how this Higgs field is twisted. And as given in the discussion, we can consider some of the topological properties of the surface at infinity in the Higgs vacuum we're choosing. This phi basically lies on a sphere. Since we're in the Higgs vacuum, it's of constant magnitude A. So the non-trivial homotopy of this sphere, a second homotopy to be precise, of this sphere gives us the quantization we are looking at.
Hi, Devashish here. I'll now discuss the tutorial problem for our project. So if you recall, we had derived the laws of conservation of linear and angular momentum in class. So this was derived in class, and this was a tutorial problem where Pm is the mechanical momentum, L is the angular momentum, and this was done from Maxwell's equations. Now we'll use an alternative approach, which was discussed in the earlier section. So the question is to derive the law of conservation of angular momentum using Noether's theorem. So you may refer to the example solved above, like in the earlier section, for reference. So the hint given here is that to naturally obtain the law of conservation of angular momentum, we consider the symmetry of the Lagrangian under infinitesimal Lorentz transformation along with gauge transformation. So yeah, this is the Lagrangian for EM fields. Yeah, and the coordinate x mu under a infinitesimal Lorentz transformation would change as follows. So the matrix Lorentz transformation matrix can be approximated to be identity plus a infinitesimal antisymmetric matrix omega mu nu, which has parameters of the transformation, and this is arbitrary, but much each element is much smaller than 1. So delta, which is the change in x, is given as follows. A similar analysis and a Taylor expansion in the coordinates gives us this expression for the change in A mu. Here chi is the gauge field, and omega mu nu is again the infinitesimal antisymmetric matrix for Lorentz transformation. Yeah, we here choose chi to have a particular form to ensure that delta A mu is gauge invariant, which in turn gives this form. This was also discussed earlier, so I'll just move to the main part. So the main part is substituting the expression of delta A mu in the expression for the change in the Lagrangian, which we want it to be 0 because we expect it to be symmetric under Lorentz transformation. So yeah, so these steps I've already discussed earlier. I've substituted the expression for delta mu simply here. And yeah, note one thing, I have over here I have lowered an index of omega using the metric. Okay, so now if you have a close look at this, the first term looks like a part of the canonical symmetric traceless stress energy tensor, which was theta. So we actually add the second half and subtract it. So we get one copy of the stress energy tensor and an extra negative term. So we now need to make sense of the second term. Also, one thing which we can do is, since kappa and sigma both are dummy indices, we can very well swap them. And over here, I've swapped them and then again use the antisymmetry of omega kappa sigma to equate it to minus omega sigma kappa. So these are just 2 steps. Yeah, then adding these 2 equations, we get a new equation where the first term is actually what we expect beforehand from what we had done in the tutorial. And the second term should essentially reduce to the source terms for the change in angular momentum. So we start simplifying this. First, we take the total derivative in. If in fact it turns out that the derivative of if we apply chain rule, derivative of the first term in the brackets, g times x is actually 0, and it's easy to verify. And the only thing that remains is the derivative of the second term, which I had computed in the earlier section. So I've directly used the result from equation 71. It's linked here. And it actually gives us the form that we want. So And yeah, this is equal to 0. So we have actually derived conservation of angular momentum in presence of sources. So yeah, that is it. Thank you.